In section 1.8, we're going to talk about linear transformation. But before we get started, let's quickly review functions that we first came across in an algebra class, okay? So let's say that I have a function like this. It's defined as f from R to R. So first of all, before we go any further, what does this mean? This means that the domain is all real numbers. And the range of, and not the range, sorry, and the codomain, this is called the codomain, is also all real numbers. So let me graph that. So here is where we have, this is going to be my domain. I'll call this R because that's all real numbers. And here is my codomain. And this is R. A good way to think of a function that we first come across in an algebra class is like a formula. It takes some input and gives you some output, okay? The only key thing in a function is what? For each input, you can only have one output, okay? Now, so here's my function, and the function is defined as follows. It is f of x is equal to x squared. So that is my function, okay? So what does it do? Well, this function takes every x in the domain, okay, and it maps it to, or assigns it the value of x squared in the range, okay? So it'll take this value and assign it a value here, and this is x squared. So this is my function that we have. Okay, that's what that does. So it transforms x into x squared. That's what it does. And that's what we are going to do. Okay, except in our case, instead of having real numbers and real numbers on either side for the input and output, we're going to have vectors. Okay, that's the only difference that we are going to come across. Instead of working with real numbers, we're going to be working with vectors. Okay, so one more thing I want to point out about this specific function. If you notice what is special about this function, doesn't matter what your input is, what the values in the domain are, the output is going to be x squared, right? So the output is always going to be what then? It's always going to be positive, okay? So we are not going to get all real numbers back. We're only going to get the positive numbers back. So in this case, we're only going to get a subset of the real numbers. We're not going to get all of them. We're only going to get so these are the positive real numbers. Or I should say non-negative real numbers is better because we could get zero back, okay? So let's say it's non-negative real numbers. So in this particular case, for every x in the domain, for every real number, we're only going to get positive, non-negative real numbers back. So we're not going to get all real numbers. We're only going to get a subset small. So we call this pink set that I have highlighted here, we call this the range. Okay. So the codomain is everything we can possibly get back, but the range is actually everything we get back. Exactly. Okay. So the range is a subset of the codomain. Okay. So that's a quick review of functions. Let's go ahead and talk about a transformation, and then we'll talk about linear transformation. Okay. So we'll start by first talking about a transformation. Okay. So here's a definition of a transformation. A transformation, sorry. And I'll put in parentheses, you can think of it as a function, t, from Rn, so it's going to take all the vectors in Rn that have n components, to Rm, and it's going to assign a vector in Rm which has m components, is a rule that assigns each vector x in Rn, each vector x in Rn, a vector t of x. Okay, so keep in mind this is also a vector, so you could put a bar there, but that gets tedious to write, so I'll just write t of x in Rn. Okay, so just like to relate it to what I wrote down earlier with functions, so we have some transform t that takes each vector from Rn and assigns it to a vector in Rm. Okay, so that's what it is. And sometimes, just for ease of writing, sometimes books will write it this way. They will write it as x, the vector x gets assigned to t of x. Okay. And visually, what this basically means is just like we drew that picture earlier. This is my vector x, so this is my domain. And here is my codomain. And within the codomain, I have a range that it's going to get assigned to. So this is going to be my range. Okay. So it's going to take this x and assign it to t of x in the range. Okay. And that's what this is going to do. So that's my transform t. Okay. We call this t of x. Okay. Let me write that down, a couple things, couple notes. So this is very similar to what we had with functions, except we just had real numbers, but now we have vectors, okay? So let me put a couple notes down. One, okay, t of x is called the image of x under t. Okay, so we call t of x the image of x under t, okay? Or you can say t is transforming x into t of x, okay? Two, okay, the range, just to be clear, the range is the set of all t of x's, all outputs. You can think of that, or you can think of it as the set of all linear combinations. Actually, let me write that later once I talk about matrices, so let's not go there for now. We will just leave it like this for now, okay? All right. So out here, by the way, this was Rn, my domain, and this was my codomain. Okay? So let's take a look at some examples of this so you guys can see. So I'll just start with a couple simple ones. So let's say we have a transform t from R2 to R2, and it's defined as t. So it's going to take a vector in R2, which has two components, and give you a new vector, which looks something like this, x1 plus x2 and x1 minus x2. So this is the definition of the transform. Just like when we did functions, this was the definition of the function that told us what it's going to do to each x, right? Out here, it's going to take each vector in R2 and create a new vector, which also happens to be in R2. So here's an example of this function. So what is the image of the vector 1 minus 2? Actually, let's do something. Yeah, let's do 1 minus 2. So they've asked us to find the image. They find, actually, I'll just do it so I don't have to write it. So let's do this, t of 1 minus 2. So remember, this first component is x1, negative 2 is x2. So what does it do? Well, it takes x1 and adds x2 to it. So I'm going to take 1 minus and add minus 2 to it. And the second component is you're going to take x1 and subtract x2 from it. So if you do the math, we get negative 1 and 3. So this vector 1 minus 2 gets transformed to this vector under T. So this is the image of 1 minus 2 under T. Okay, so we say that minus 1, 3 is the image of 1 minus 2 under T. Okay, so that's an example of a transform. Here's one more. So let's say this time I'm going from R2, we're taking vectors in R2 input, and we're going to get a vector in R3. And it's defined as follows. So we have x1, x2, and we're going to end up with x2. We're going to end up with x1 minus x2 and x1 plus x2. So this is the definition of the transform. So let's take a look at an example and see what happens to a vector in R2. So let's pick a vector in R2. So let's say I pick minus 1, 1. So this is my vector in R2. x1 is minus 1, x2 is 1. What happens to this vector? Well, according to this, we get x2 as the first component. So we get 1 because x2 is 1. Then we get the difference of the two vectors. So we get minus 1. We get this x1 is minus 1. So we get minus 1 minus 1. So we get negative 2. And then we add them together. So if you add these two together, we get 0. So that's how that vector is going to get transformed under that one. Is that okay? All right. Now let's take a look at one last example, which will lay the foundation for what we want to do next, okay? Talk about matrix transforms, okay? All right. So if you notice in this last example that we just did, we had this as a transform, right? x2, x1 minus x2, and x1 plus x2. That was the definition of a transform. I'm going to just split this up a little bit, okay? So I can write this as what? There's no x1 in the first component. There's one x1 in the second, and then you have x1. And I'm going to add up the x2. So we have x2 minus x2 and x2. Okay. I can pull out an x1 from the first vector here. So I get 0, 1, 1. And I can pull out an x2 out of the second vector. So I get 1 minus 1, 1. Okay. This looks like a linear combination that we came across before. What is a linear combination? A product of a vector and a scalar, correct? And you add them all up. Okay. So you can think of this as now, so you can say I have T, which is made up of x1 and x2. Okay. And that's going to give us what? What's another way to write this? And you can also think of it as a linear combination, or you can think of it as a vector equation, correct? If it's a vector equation, we know we can rewrite this as 0, 1, 1, 1 minus 1, 1, and we have x1 and x2, correct? That's how we write vector equation. That's how we take a vector equation and make it into a matrix equation. Okay. So in this case, I can rewrite this as 0, 1, 1 minus 1, 1, 1, and I can call this x1 and x2. Okay. So basically, we broke this down a little bit further and wrote it in terms of a matrix. Do you see that? Okay. Out here, it was in terms of a vector. Okay. So now I can do better a little bit. I can also think of this as the matrix A and this as a vector X, okay, that we start with. This is X. So we can write it as AX. So we can change this transform into a matrix vector product is what we are trying to get at. Is that okay? So we're going to rewrite the transform as a matrix vector product. Okay, and that's what we're going to do next. And that's going to be our main focus going forward. Okay, so this is C. So we're going to talk about matrix transformation. just to clarify, in the last example, this and this are the same. Oops. They're just different notations. And, we've talked about it. We can write things as a vector equation, as a matrix equations, and so on, right? To just keep that in mind. They're all the same things, okay? So let's define the matrix transform. If A is, excuse me, is an m by n matrix, then the transformation sorry about that. Then the transformation T from Rn to Rm, okay, defined by T of x is equal to Ax, is called a matrix transformation associated with A. And like I said, this is going to be a main focus going forward, okay? So that's a matrix transformation. All right, so let's take a look at an example of a matrix transformation. Okay? We'll take a look at actually a couple examples, but let's start with this one first. So let's say that they've given us this A is 1 minus 2, 3, minus 5, minus plus 10, minus 15. And then they've given us the vector U, which is 2, 3, 1. Then they've given us the vector B, which is 2 and negative 10. And finally, they've given us a vector C, which is 3 and 0. So they've given us a whole bunch of vectors. Some of them are in R3, some of them are in R2. This matrix over here is 2 by 3. Okay, that's what it is. All right. Okay, so there's a transform that's defined as this from R3 to R2. So it takes a vector in R3 and gives you a vector in R2, okay? And from R3 to R2 and defined by T of x is equal to Ax. So this x is in R3 because that's what it's doing. It's taking a vector in R3 and giving it. When you multiply this, you're going to end up with a vector in R2. Okay, so that's what's going to happen. So that's how we've defined it, where A is this matrix. Okay, so the first question they've asked us is, they've asked us to find the image. They've asked us find the image of U under T. So in essence, they've asked us, okay, what is the output if the input is U? So that they've asked us to find that is find T of U. That's what they've asked us. Okay, so let's do that. So to find T of U, what are we going to do? This is how we've defined our transformation. Instead of x, we have U, so you're going to take A times U. We know what A is. A is 1, negative 2, 3, negative 5, 10, negative 15. And we're going to multiply that by U, which is 2, 3, 1. We know how to multiply matrices and vectors. We can use row column multiplication. Correct? So if I do that, and by the way, if you look at it, this matrix A was 3 by 2, I'm sorry, 2 by 3, and U is 3 by 1. It's got 3 components. So when you multiply this, you're going to end up with 2 by 1, which is in R2. Okay, it's got 2 components and 1 column. Okay, So we're going to get 2 minus 6 plus 3. And the second one is going to give you minus 10 plus 30 minus 15. So if you add them up, you get -1, and then we get 25. So that is the image of u under T. That means this vector u gets transformed to this vector in R2. Okay. The next question they've asked us is find X in R3 whose image is B under T. Okay. So they've asked us, they've asked us what vector X will give us B. So we've done problems like this because what's another way to write this? Well, T of X is the same as AX. That's how we defined it, recall that, is equal to B. So we are basically just solving a matrix equation. And when we solve a matrix equation, what do? We ref it or we ref it, correct? That's all we do. So that's all we need to do here. Put it into a matrix equation and ref it, okay? So we're going to put that into a matrix. Our matrix was 1, -2, 3, and then we had -5, 10, -15, and our B was what? 2 and -10. So we're going to ref this because we're taking AX. A was this, and B is that we're looking for X. Okay. So when we ref it, we'll end up with this. This is just ref, not ref. We end up with 1, -2, 3, and 2, and we get a row of all zeros. Okay. So now they want us to find an X. Because we have a pivot here, we have how many free variables here? We have 2 free variables. Is that okay? That's all right. So we didn't find one X, we actually found a whole bunch of X's, just so you know, because of the free variables. Okay, so let's write down, at least find one of them, because they wanted us to find an X, right? So typically a solution from here, from the first row, we know that X1 is going to be 2 plus X2 minus 3X3. Oops, 2X2 minus, I moved these two to the other side and did that. So that's what X1 is. So my vector X, which is made up of X1, X2, X3, because remember X is in R3, so it should have 3 components. The first top line is 2 plus 2X2 minus 3X3, then we have X2, and then we have X3. So this is our vector. Now, all we have to do here is pick X2 and X3 because they're free variables to anything. Remember, they want us to find one of these vectors. We can write this way. I have 2, 0, 0, plus I have 2, 1, 0, X2, plus I have -3, 0, 1, X3. When I add these guys, I should get this back, okay? I just broke it up. So now to find, that's my X. They wanted us to find X and X, but I can pick a particular X. I can take X2 to be 0, and I can take X3 to be 1 because they're free. I can take them to be anything. So what does X look like? Obviously, I could have taken both X2 and X3 to be 0, but let's mix it up. So you can use either this or this form, doesn't matter. Replace X2 with 0 and X1 with 1. So we get 0, 2 minus 3 is -1. Then we get 0 and we get 1. So that's one example of a vector that'll map into B. So B was what? 2, -10. Okay. And here is another one. And we can do a whole bunch. I'm just going to give you 2 examples. Let's say X2 is -1 and X3 is -2. Okay, so what does that one look like? Well, if I plug that in, I get x is going to be what now? So we get 2 minus 2 is 0, and negative 3 times negative 2 is 6. And then we get negative 1 and negative 2. So that's my other example. So in both of these cases, visually, what's happening? We are taking some vector in our domain, and the vector we are taking is this x minus 1, 0, 1. I'll call this x1. I'm sorry, this is a vector, so I'm putting a bar. Remember, these x1s are not vectors. These are not vectors. These are components, but I'll put a bar here. And I'm going to take another vector, x2, which is 6 minus 1 minus 2. These are in my domain. And I'm going to map them, and they both map to a vector 5, 2, 10. So this is my vector b, which happens to be 210, 2, negative 10, sorry. Okay, so both of these vectors map to the same output. You can think of it as, okay, just like if you were to go back out here and look at our function, the one we started with, if I take x1 to be 2 and x2 to be minus 2, and out here we have a 4, what happens? When you square x1, we get 4, and when we square x2, we also get 4. So they both map to the same value, which is okay when we define functions. For each x, you have one y. So that's perfectly fine. Okay. The next question they could ask us out here is so this is a very important question. Okay, so they've asked us, is there, okay, I'll capitalize the word n, an x, okay, for which t of x is equal to b. Okay, they've asked us that. Well, it's the same b. What did we find? Because we found free variables, did we find 1x or did we find infinite x's? So we found infinite x's. So because we had free variables, this implies there are more than 1x. Okay. So this question really is a question of uniqueness. They're asking if it only had one solution, then it would be unique. But in this case, we got more than one solution, so it's not unique. So it's a question of uniqueness. So is there an x that does that? No, there's more than one x, okay? Not just x, but there's more than one x. The next question is, they've asked us, is there an x, okay, for which t of x is equal to c? So this would end up becoming a question of existence. Okay, and you'll see that. So this time, instead of ending up with B, we're going to end up with C. So let's do the same thing we did before. Plug it into a matrix. Oops, this is 5, sorry. And then we have 3, 0. So we are doing the same problem that we did here. It's the exact same problem, so I'm not writing all the details, but instead of getting B, they want us to see if we get C. Is that okay? So we're going to ref it again. So if I ref it, I end up with this 1 minus 2, 3, 0, and we get 0, 0, 0, 1. Because there's a pivot in the last column of the augmented matrix, this tells me that we have no solution. So this tells us there's no x that'll do that, okay? No x, whose image is going to give us C. So what does that mean visually? So let's take a look at that. So it means that I can take some x. In our case, the x was, they want us to find some x, sorry. Okay. And what does this transform do? It takes each x and transforms it, gives us the image, right? So which is some t of x. That's what it does. Is that okay? So it takes some vector x, and these vectors are in R3 and gives us a vector in R2. So all of the images, if you take all the images from the domain, that gives us the range. Okay, but what happened this time? There was no x that gave us C. And what was C? 3, 0. It didn't give us C. So that means what it's saying is that there is some vector that's outside my range. It is in the codomain, just so you know. Okay, it is in the codomain, but there's no vector that maps to this vector. Okay, so all the vectors that map are in the range. And this is a vector, there's a vector in R2 that doesn't get mapped. So there's no X that'll map to that. Okay, so that's what visually it tells us. All right, so now that we saw some of these things, one of the cool uses of transformation is in computer graphics. You can, in computer graphics, when you're playing computer games and things like that, the game is constantly changing perspective, it's constantly changing perception, and it's enlarging things, shrinking things, and things like that. And how is that all done? That's all done through matrix transformation. There's special matrices that will, when you multiply by a vector, it'll transform that vector, it'll rotate it, it'll shrink it, it'll enlarge it, it'll shear it. It'll do a lot of different things to that vector. And those are just different types of transformations. So I'll give you a couple examples of those, okay? Just some examples. And these are all used in computer graphics. Computer games would not exist without a lot of matrix transformation, just so you know. Because all the math that's done to move things in a game, they're all done using matrix transformations, okay? All right, so this was C. This is D. So these are some examples of matrix transformation. Okay. And again, there's lots of them. I'm just going to give you a small subset of them. So let's start with the first one. So let's say you have a transformation like this. T of x is R 0, 0, R of x. Okay. So first, let's see what it does, and then we'll write down in words what's happening. Okay, first let's see what it does to some vectors. So a good way to start is let's just pick a couple vectors and see what happens to them. Okay, so here are some examples. So let's say if I take a vector x, let's say it is 2, 8. Okay, and I'm going to take r is just a constant, just so you know. Out here, r is just a constant. Actually, let's use a. Yeah, we can just stick with a and b instead of r. Okay, so this is a and a. So a is just a constant. So let's pick a. I'm going to pick a to be 2. Okay, so I'm going to change this a little bit. I'll make this a 3, something small. Okay? So a is going to be 2. So my transformation is what? T of x is what? 2, 0, 0, 2 x. So let's see what happens to this. So we take t of 2, 3. What does that mean? That means you take 2, 0, 0, 2 and multiply it by 2, 3. We know how to multiply matrix and vectors, right? Row times column, row times column. So we get 4 and 6. So let's see graphically what happened out here. So if I were to graph this, I'm taking the vector 2, 3. So here's the vector 2, 3. So this is the vector we are starting with. This is like my input, my x. What is happening? What is the image of x under this transformation? What happens to x when you apply this transformation? Well, it becomes a vector 4, 6. So what does that look like? Here's 4 and here is 6. So what did we do to that vector? I know it's not drawn correctly, but it should be in the same line, okay? So what did we do to that vector? We stretched it, in essence. Do you follow? We stretched it in the x direction and also in the y direction. If a was between 0 and 1, then we would shrink it, okay? So what this does, what this transformation does, it's a dilation. We call it a dilation if A is greater than 1, and it's a contraction, it contracts if A is between 0 and 1. So it'll either stretch it or shrink it depending upon what the value of A is, okay, in the X and the Y direction. So that's what it does, okay. So that's pretty cool, and it's stretching and shrinking by a factor of A. So if you're in a computer game and you want to enlarge an image or something like that, that's what you would do. You would multiply every pixel of that image by a matrix and it'll enlarge it, okay. Here's another example. So let's say we have T of X is given by 1A, 0, 1, okay, and we have X. Now again, we'll leave some room to write down in words what it does, but let's take a look at an example and see what's happening visually. So I'll just take some random vector X. This time I'm not going to write all the steps like I did last time. Let me just do T of X. My vector X that I'm going to use is, let's use 1, 2, okay? And I'll take A to be, let's say, 3, okay? So what will this do? It'll take 1, 3, 0, 1 and multiply it by the vector 1, 2. So if I do that, what do I end up with? So we'll do row times column. So we get 1 plus 6 is 7, and then we get 2. That's what we get. So let's see visually what happens, okay? So let's graph it. So this is like your x1 and x2. So we have 7. This is 2 and 1, sorry. Then we have 1, 2. So what does it do? It takes this vector 1, 2. So let's start with that vector 1, 2. That's this vector. And what does it transform it into? So this is my X. It's going to get transformed now, okay, into this vector 7, 2. So what does that look like? 7, 2 is right here. So you can see this is called a horizontal shear. We're horizontally stretching the vector. Vertically, it's the same. It's still 2, but horizontally, 1 became a 7, okay? So this is called a horizontal shear. The next example, and there's so many, you can do reflections, you can do rotations, you can do all kinds of stuff with these matrix transformations, and they're all used in computer graphics, okay? I'll do one more. If you have 1, 0, I'll use a B this time since it's a little bit different, okay? X. I'm not going to do an example. If you look at this and the previous example were the same. Instead of getting a horizontal shear, you're going to get a vertical shear. It's going to stretch it vertically. Horizontally, it's going to stay the same. Okay, so that's a vertical shear. And I'll do one last one, which is the interesting one. I like this one. Okay, so this one, we have T of X is equal to, this is going to be interesting. We have cosine of theta, sine theta, and then we have minus sine theta, and then we have cosine theta X. And theta clearly is some angle. Is that okay? So let's see what happens first by doing an example, then we'll write down what's going to happen. So let's say, I'm going to say let theta equal to, let's do pi, and just to show you what's going to happen. Okay, pi is a good easy value to work with. Okay, so let's see what happens to one of our vectors. So if I take some t of, let's start with some vector. So let's say I'll use some negative values now. So you have 1, negative 2, and 3. Okay, now we're going to transform this. We get cosine of pi minus sine of pi, and sine of pi, and then we get cosine of pi, and we're going to multiply that by negative 2, 3. So what does this transformation do to this vector? So let's see what happens. If you know from your basic trig, cosine of pi is -1, sine of pi is 0, this is -1, this is 0. So in essence, we just have what? -1, 0, 0, -1, and we have negative 2, 3. So if I multiply these, I get row times column, so I get 2 and negative 3. Okay, so let's see visually what's going on with this. All right, so if you were to graph this, oops. Okay, so we have -1, -2, and then we have 1, 2, 3, we have -1, -2, and -3. So we're going to start with a vector -2, 3. So that's out here, -2, 3. That's all the way up here. That's this vector. So we're going to take this vector. This is my vector x. What does this transformation do? When I multiply by this matrix, what does it do? It transforms that vector to 2, -3. Okay, oops, I forgot to put vector values here, 1, 2. So 2, -3. So that's this. So it transforms that vector to this vector. So what did it do? It basically rotated that vector by pi radians. Okay, so it rotated that vector by pi radians. So whatever this angle is, you can, whatever angle you want to rotate by, you take theta to be that value, and then multiply whatever vector you want to rotate by that angle, by this transformation matrix, and you will get that rotation. So this basically does a counterclockwise rotation by theta. So this does counterclockwise rotation by theta. So this is really cool. You can see how we can use simple matrix vector multiplication to manipulate the pixels in a computer of an image or of a person in a computer game and make them do whatever we want. We can shear them, or we can do a contraction, so we can change the perspective in the sense like when we shrink something, it appears way far away in the background and so on. So we can manipulate them many different ways. I have just given you a small subset of this. You can do all kinds of other stuff. You can do reflections. You can do all kinds of other stuff with this. Is that okay? Okay. So, and anytime they ask you, what does this transformation do? Just pick some vector, transform it, and see visually what happens. There are a couple questions like that you actually, let me do one really quick. So here's one. So they've given you two vectors, u and v, 5 and this is problem number 13. Okay. And they've asked us to show what happens when you multiply by this transformation, -1, 0, 0, -1. Okay, so they're asking us to do that. I think that's what we just did. No, we didn't do that. What did we do? Oops. Yep, that's exactly. So that's kind of a rotation. So let me do a different one. So that would have been a rotation in that example, okay? This is a rotation matrix when you want to rotate by pi, okay? Or you can also think of it as a reflection about the origin. Do you guys follow? You can think of it as a reflection about the origin. Okay, so you can think of it a couple different ways there. All right, let's do 15. So we have 0, 1, 1, 0. So we have t is defined to be 0, 1, 1, 0, x. They want us to describe what happened. What does this transformation do? And they've given us two vectors to manipulate to figure out what does that do, okay? So 5, 2, and -2, 4. So let's see what happens. So let's say t of 5, 2. And see what it does. And then let's take t of -2, 4. So we're going to multiply both of those and graph them and see what's going on, okay? So out here, when we multiply row times column, we get 2, row times column, we get 2. So it looks like the x and the y components are getting swapped, if you can see. Well, let's see what happens here. Row times column, I get 4, row times column, I get this. Then you can see the same thing. The x and the y components are getting swapped, okay? So let's see visually what that actually looks like, or how we could describe it. So we have 5, 2, -4. Okay, so let's start with the first one. What does first one become? 5, 2. This is 5 and 2. So what happens to this vector? Well, this is u. What happens to u? It becomes 2, 5. 2. So that's what transforms 5, 2 becomes 2, 5. So if you think about it, what do you think is happening? Okay, let's do the next one so you can look at both and see. Maybe that'll help. -2, 4. That's this vector. And what does that become? 4, 2. 4, 2. Okay, so, no, 4, -2. Sorry. 4, negative. This is -2, 4, and then we have 4, -2. So if you notice, what's happening here is you're swapping x1 and x2 here, or you can think of it as you're reflecting all of when does that happen? If you remember, this happens when you reflect a point about the line y is equal to x. So here is the line. Normally we call it y is equal to x because this would be x1 and this would be x and y, but now we have x1 and x2. Okay, so this would be the line x2 is equal to x1. So if you notice, this point gets reflected and becomes this point, and this point gets reflected and becomes this one. So it's giving us a reflection about that line. So that's what that matrix transformation is doing. Okay. All right. I hope I convinced you some of this stuff is extremely important in computer graphics. I had a student who took linear algebra from me at least a good 20 years ago. And he did not do so well in it, and he was really frustrated with the class. And I remember many years later, I think close to 5 or 7 years later, he actually came and visited me when he was back on campus. And he told me he was so grateful that I taught him linear algebra because he uses it all the time when he's doing computer graphics. And he was just like so thankful that I taught him linear algebra. So it is something that's very, very useful. Okay. All right. There are two more things I need to do in this section. This was D, E. So the title of this, so far we've been talking about transformations and matrix transformations, but the title of this section was linear transformations. So we haven't really focused on that, so let's do that. Linear transformation. Okay. So from going forward, I'll just call it LT because we're going to write it so many times. We just don't want to keep writing it again and again. Okay. Basically, linear transformation will transform a line into a line. That's kind of what linear is usually word for line. It represents a line. So it will transform a line into a line. Okay. So it's a special type of transformation. So let's define it. A transformation T from Rn to Rm is a linear, I'll capitalize because going forward, this is what we are interested in, is a linear transformation if it satisfies two conditions. The first condition is T of u plus v. just so you know, what we're going to write down is exactly what we say it's a linear operator. I'll come back to that. Let me just not confuse you. Let's do this. So when you take when you transform is sum of two vectors, then you can transform the first vector. You get the transformation of the first vector plus the transformation of the second vector. Okay. For all u, v in Rn. Remember, u and v are my inputs. My inputs are in Rn. They're in my domain. And 2, t of c comes some constant times u. You can pull that constant out, so you get t of u. Okay. For all u in Rn and any scalar c. Scalar means just a number, scalar c. Okay. So any transformation that satisfies these two properties, we say it's linear. Okay. Let me write down a few notes. So not all transformation are linear, just so you know. Okay. So the first note I want to talk about, just to give you some correlation to things you've done before, a linear operator. In math, a linear operator is anything that literally satisfies these two conditions. And you've come across many over your lifetime in math. So let me remind you of a couple. The three that you've come across that you should know. Limit is a linear operator. Why is that? If you remember, if you take the limit of f plus g, what do we get? We get limit of f plus the limit of g. And if you take limit of some constant times f, you can pull that constant out and you get this. So limit is a linear operator. Then we have derivatives. Well, let's see. When you take a derivative of f plus g, you can get derivative of f plus derivative of g. You can do term by term. That's all this is really saying. This is saying is you can transform it term by term, in essence, this and this. That's what we do. Okay. And when you take derivative of a constant times a function, the constant comes out and you just take the derivative of the function. And integration. So these are the three you've come across that you should be familiar with. If you take integral of f plus g, you get integral of f plus the integral of g. And if you take integral of c times f, the c comes out, then you get integral of f. So these are the three linear operators you've come across. And we are just extending that concept now to vectors and transformations, okay, that involve vectors, okay? The next thing I want to point out here, okay, when you look at the two properties they've given you, what will happen if C is 0 in the second condition? If C is equal to 0 remember, C is any scalar C. So if C is 0, C can be 0. So if C is 0, then what happens? You get T times 0 times U is equal to 0 times T of U, which becomes what then? We get T of, if you take 0 times some vector, you'll get the 0 vector, okay, is equal to, out here you take 0 times, this will give us a vector, so if you multiply it, you'll get the 0 vector. So for a transformation to be linear, what does it mean? It maps the 0 vector to the 0 vector, okay, so this implies maps the 0 vector to the 0 vector. If the input is 0, the output will be 0. That's something special about the transformation. Is that okay? So you have a couple choices here. Anytime you want to show something is a linear transform, you have to satisfy these two conditions. And so both of these conditions can be combined into one. So to show a transform is a linear transform, we can combine those two into one. So you can say T of, let's say we have A times U plus B times V will give us A times T of U plus B times T of V. So we've combined those two conditions that we need to show a transform is a linear transformation into both of these into one. So we only have to check one then. Is that okay? So that's something to show it's a linear transformation, show this happens, okay? Now, to show something is not a linear transformation, to show a transform is not linear, not a linear transformation, then we have a couple options. We want to show that this is not true. By the way, in this, when I'm writing this down, this is not true. A and B are scalars, okay, just like it was C before. Just hopefully you guys know that. We can show this, or we can give a counter example. Or actually, no, one other thing. Or and a good one to show is, or you can show that 0 doesn't map to the 0 vector, or you can give a counter example. And I'll show you how to do that. Okay. So to show something is not a linear transformation, you have to do one of these three things, okay? To show it is a linear transformation, you can do this, or like I said, you can show each of these individually. It's up to you, okay? All right. So the next few examples are where they've given us a transformation and they've asked us, is this a linear transformation? So we want to check those conditions. So let's start with the first example. They've given us this, they've taken t, x1, x2 is equal to 1 plus x1 minus x2. Okay. Well, if you wanted to, so they've asked us, is this a linear transformation? Okay. I always check the 0 case right away. You know, if you know it's a linear transformation, then you can do this. But eventually, once you do enough problems, you'll know that if it is or it isn't. Okay. But let's do that. So it should map the 0 vector 0, 0. We should end up with 0, 0. So let's see what happens. We get 1 plus 0 minus 0. So we end up with 1, 0. So this is not the 0, 0 vector. Remember what we said, 0 vector always maps to the 0 vector. So this clearly implies that not a linear transformation. So whenever you have a singleton constant, it's never going to be a linear transformation because that'll never map to a 0. Is that okay? All right. Here is another example. They've asked us, is this transformation T of X, you have X1, X2, and X2, a linear transformation? Okay, so how do we do this? Well, we could do the same thing that we did a minute ago. Do you follow? Okay, so let's take a look at, if I take the 0 vector, and by the way, you know, in algebra, if I give you a function like this, 2x plus 1, is this a linear function? The degree is 1, so it's linear. If I give you a function like this, is this a linear function? The degree is 2, it's not, okay? So technically, just from your knowledge of algebra, because you're multiplying x and x, you're multiplying this is degree 1 and degree 1, so this is technically degree 2 on the top. So that's not going to be linear. It's giving me an inclination that it's not going to be linear. So let's start that. So if I use the 0, 0 vector, okay, it should give me the 0 vector. So I get 0 times 0, 0. So it gives me 0, 0. So that works. So you might think, oh, it is linear. Okay, remember, just because it satisfied that one condition doesn't make it linear. There's this whole condition to satisfy also. So let's test that. So let's take T of AU plus AV, BV. Okay. So we can do it that way. Okay. So what does this mean? Well, it means that you're going to take T of A, okay, times, remember, U is a vector. It's got two components. I should have mentioned this. This is a transform from R2 to R2. So it's going to have two components, okay? So what does U look like? Well, U is really U1 and U2. What does V look like? It is really V1 and V2. And A and B are just scalars, okay? So we get A times U1 plus B times V1, and then we get A times U2 plus B times V2. Okay, so this is my first component of my input. This is my second component. I'm multiplying each of these by A and each of these by B and adding them up. So what happens to this under this transform? You take the product of this and this, so you get A times U1 plus B times V1 times A times U2 plus B times V2. And then in the second row, we get A times U2 plus B times V2, because you just get X2 and this happens to be X2. Okay, good. Now, if you multiply it, remember what should happen. If this was a linear transformation, this should actually give us what? A times U Tu plus B times TV. This is what should happen. If it was a linear transformation, it should give us this, right? So let's see. If I multiply, I'm going to get a whole bunch of squares and things like that on the top, right? So I get A squared U1 U2 plus AB U1 V2 plus AB V1 U2 plus B squared V1 V2. And that clearly is not going to give us this, just so you know. And on the second row, we just get this. Okay? So this is clearly not equal to this. If it was, then it would give us that. Okay. And when I say not equal to this, what does this look like? So let me show you what this looks like. Okay. What are we doing? We're taking A and multiplying it by T of U. What does T of U do? Well, according to this T of U, if you replace it with U, you'll get U1, U2, and then you'll get U2. Okay. So that's what you'll get instead of X. So this will give us U1, U2, and U2. What is T of V going to give us? V1, V2, and U2. So if you add them up, I'll get A U1, U2 plus B V1, V2. I'll get A U2 plus B U2, B V2, sorry, this is V2. Is this equal to this? No, because that's what this is equal to. Do you follow? So they're not equal, so this is not a linear transformation. Okay. So I've given you two examples of transformations that are not linear. Let me give you one where it is linear, so you don't think everything is not linear. Is that okay? All right. So here's one that is linear. So they've given us this. T of x is equal to x1 plus x2, 0, and 2x1. And so and they've asked us T is going from R2 to R3, and they've asked us, is T a linear transform? Okay, that's what they've asked us. All right, so let's do that. Let's do the same thing. So again, I know I'm not trying to confuse you. I told you before, to show something is a linear transformation, it has to satisfy this condition and this condition. And both of those conditions can be aggregated into one like this. If you don't feel comfortable doing it this way, you can do them separately. In the last example, I did them together. In this example, I'm also going to do them together. I just like to do them together, but it's up to you. So we get AU plus BV, which basically means T of AU1 plus BV1, AU2 plus BV2. If this is U1, U2 because it's in R2, and this is V1, V2, okay? And then you're adding them up. So now we're going to push them into this. So what is the first one? What does it do? It takes the first component and adds the second component. So you get AU1 plus BV1 plus AU2 plus BV2. That's what, and then we get 0, and then we get 2 times AU1 x1 plus 2 times BV1. So that's what we get. All right, remember, what should this give us? If I take this vector and transform it, if it's a linear transformation, I should get this. Correct? And what does this look like? What is T of U? Well, it'll give us U1 plus U2, 0, and U1, 2U1. And what is T of V? And again, this is something I'm showing you what we are looking for so you can see. And so if we add them together, you distribute the A and add them together, you get AU1 plus AU2 plus BV1 plus BV2. And then 0 plus 0 is 0. And then when you add the last row, we get this. Is that what I have here? Oops, I forgot the A and the B here. 2A and 2B because there's B's on the outside. Okay? And that's exactly what we have here. So this is really A times T of U plus B times, actually, let me show you how we can get it to that form so you can see it. So I'm just going to combine just the A terms here. So I get AU1 plus AU2 plus BV1 plus BV2. I have 0, I get 2AU1 plus 2BV1. Then I'm going to break it into two matrices. One that includes all the A's and the other one that includes all the B's. So AU1 plus AU2, 0, 2AU1. I have BV1 plus BV2, 0, 2BV1. Now I'm going to take an A out of the first one. So I get U1 plus U2, 0, and U2U1. Out here, I'm going to take a B out. So I get V1 plus V2, 0, and 2V. If you look at it, this is really the definition of T of U. Instead of X here, we have U's. So we get ATU plus BTV. Okay. And that tells me, so this is a linear transformation. So this transformation is a linear transformation. So not all transformations are not linear. Some of them are linear. Okay. The last thing I want to talk about is a theorem. I can't remember the number. I want to say it's 10, so I'm going to put 10. If it isn't, then we'll have to fix it. Okay, but this theorem states that every matrix transformation, we talked about matrix transformation earlier. So every matrix transformation, okay, so it's written like this. If you recall from earlier, T of X is AX, okay, is a linear transformation. Okay, so every matrix transformation is a linear transformation. Okay, so just remember that. And in the next section, we will learn more on transformation. Okay, so and that'll be the last section for this chapter. Okay, you should be able to do all the assigned homework for this section now.